This video explains the design, the shear force reinforcement for the 600 mm by 350 mm cantilever beam, which is shown here. Cover to the fitment is to be 40 millimeters on all sides, and the characteristic compressive strength is 32 megapascal. So we have a beam is given. It has two supports, support at B, support at A, support at B, and there is a cantilever at C. The uniformly distributed load is 150 kilonewtons. The support has a width 300 millimeters. The distance between support A and B is 5.2 millimeter. Distance between support B and C is 1.8 meters. I also provided the shear force diagram. Now the shear force diagram, just calculating from the structure analysis. It's not purpose of this video to show the shear force diagram. I assume that the shear force diagram is known. Now we also provided the reinforcement. It is the bottom tensile reinforcement here. Over the supports where you have a tensions, you have top reinforcement. Now let's do some solutions. Now to design for this shear reinforcement, we generally start with the assumptions that we take R10 stirrups. It's a double leg fitments. And we have an area for one leg is pi by 4 times diameter is 10, so 10 square, that give us 79 millimeters square, which just rounding of 80 millimeter squares. Just easy for us to calculate later on, so we just put 80 millimeter square. Now it has two legs, so for two legs, for the shear reinforcement, we need to take the area ASV, which is the area of two legs. So this is the area of one leg, so we multiply by 2 to get the ASV. This is the area of the one fitments, that is calculated by taking the area of two fitments, so that is 160 millimeters. Now there is a one condition. Any shear examples, we need to check these conditions, whether the concrete is crushing or not, and the section is adequate. For example, this section which is provided 650 millimeters by 350 millimeters is adequate or not. If this condition does not satisfy, meaning that this concrete is crushed and the section is not adequate. So we start is the design shear strength, which is V star, which we take it from the shear force diagram, which is 437 kilonewtons, that is written here. Now this capacity factor is capacity reduction factor is 0.7, which is taken from table 2.2.2 on page number 36 on AS 3600 So it has on the AS 3600 on page number 36 on table 2.2.2, it has given capacity reduction factor 5. Now we are working with the shear, so go to the section E, and in that one we have a class N fitments providing requirement of other than shear strength limited by wave crushing, so we take 0.75, but we have R fitment, so we take it 5 factor 0.7. So that is 0.7 here. Now VU maximum, the oscillant standard has provided the equation for that on page number 116 on clause 8.2.3.3. we have a equation to calculate the shear strength. These big equations are written here. We are not at the transfer, so we just need to take it VU maximum, this equation that is copied here. Now 0.55, that's big equations. Now I will calculate those values one by one. Now d0 equal to dB, that is nothing but 650, which is your depth, 650 minus the cover. Let me draw the figure here that will explain everything here. So if you like to calculate this D0 or D, so if you take this reinforcement here, that will measure from here to here. So this is the D0 or D. Now this length is given as a 650. This cover is given 40. And we have a stirrups, that is stirrups goes here. So this stirrups has a diameter, this is stirrups diameter, that is given 10, that we assume here R10, so that is 10 millimeter, and this is the radius of this reinforcement, 28. So we have a reinforcement at the bottom 28 millimeters. So this is 4 bars and 20, so 28 is a millimeter. So we have this value 28 by 2 because this is measured from reinforcement. So this distance can be calculated by 650, take away cover 40, take away these stirrups 10 millimeters, take away 28 by 2, it gives us 586 millimeter. Now after calculating this d, because we need to calculate this this value d0, please note this is d, not b. All right, after that we calculate this one. We need to calculate dv. Dv is nothing but that is dv is defined as a effective shear depth. Effective shear depth is given in the clause 8.2.1.9. we can write these 3 lines, but these 3 lines is basically saying that it should be taken maximum of 0.72 d or 0.9 d. Now that is written here. Now maximum 0.7 times d, 650, depth is 650 given here in the question is 650 times 0.9, and we just calculated small d 586. We substitute this one, we take maximum of 468 times 527. The maximum value dv, which is effective shear depth, is 527 millimeter. Taking pre-stress in the example, so we take pv equal to 0, theta v equal to 36 degree, that is given in the Australian standard, that is the angle of crack. On clause number on page 119, on clause number 8.2.4.3, we have a theta v value is 36, so we taking the theta v constant value, that is written here. So we take this theta v equal to 36, alpha v equal to 90 degree. So theta v is nothing but just the angle of crack. Theta v is the angle of fitment with the longitudinal axis. So alpha v, we have a fitment 90 degree. Alpha v equal to 90 degree because we have a fitment which is 90 degree to the longitudinal axis. So cot 90 degree is given cos 90 over sin 90, 0 or 1 equal to 0. So we substitute all these values in this equation. 0.55, fc is 32 given in the questions, fc dash is 32 given in the questions. 350 is the bv, is the width of the beam, which is 350 millimeters given in the questions. 527, which is dv, effective depth of the beam, we calculated 527 times theta v, cot theta v is 36 degree, plus cot 90, 1 plus cot square 36, and pv is 0. Now if you simplify this one, and please note cot 36 is 1 over 10, so 1 over 10 36 in your calculators. Simplifications give the answer in the newtons, divided by 1000 given the answer in kilonewton, which is 1544 kilonewton. Now we need to calculate the 5 VU maximum, so we can have a 0.7 times this calculated value. We just calculated 1544 millimeters, 1454 kilonewtons, times by the capacity factor 0.7. we just noted capacity factor 0.7 from table 2.2.2, so we use 1081 kilonewton. Now we compare this one, since we start, which is we predicted 437 kilonewton, which is less than the 5 V maximum, which is 1081. So the concrete will not cross, and the beam size, which is 650 by 350 millimeters, is adequate. Now we need to find the minimum fitments. What is the minimum fitments? The spacing of the minimum fitment. The way we're gonna start is going to look at where we're going to look at the shear force diagram. When the shear force diagram has a 0 or minimum less shear, this is maximum. Near the support, it has a maximum reinforcement. So we are looking for the zone where we have a positive bending or where we have a low shear low design shear force, so that we're going to focus on. Now for this case, we can find it out minimum shear capacity, that is VU mean, and then VU mean equal to VUS plus VU mean. Now VUS is nothing but the shear capacity of the concrete, which is VUS, and that shear capacity of the concrete is given on page number 117. on page 117, we have a clause 8.2.4.1. it has given the kV, BV, dV, square root, FC dash. They have a conditions given. Our examples is not fall in any of these conditions, but you can read this one. It's about the concrete is should not be more than 65 megapascals. The fitment strength is 500 megapascals, and the aggregate particle size should not be less than 10 millimeters. So there are three conditions. We don't have these conditions here in this example, so we can use these equations. Now there are few parameters that we need to calculate. Assume that ASV greater than S and ASV minimum greater than S, so we can calculate the kV. We need to assume this one. So the kV is it can be found in the page number 119 in clause 8.2.4.3. we have a kV kV. We have two equations. If the S is both side cancel, then ASV less than ASV minimum and ASV greater than ASV minimum. So we assume that our fitment area is greater than the provided ASV min. In that case, we take kV equal to 0.15. We assume that one, but we will check that assumption later. We check this assumption whether this is valid or not. We can check this one later. So in that case, VUS is equal to kV, BV, dV and square root FC. kV is 0.15, as I mentioned. It's taken from the clause 8.2.4.3, and kV is equal to 0.15 by taking these assumptions. BV is 350. BV is 350 millimeters. dV 527. We calculated dV 527 millimeters. So once you know this capacity of the shear capacity of this concrete, which is 157, next we will look at how to calculate the minimum steel shear capacity in the next video. Thank you.